Hi, my name is Ehiane, and today I will be going through a project that I made called TreeInspect. Now, before I get into this, I want to give you a little bit of backstory on why I even built this and why it is the way it is. So I vividly remember in my sophomore year of university, I got introduced into data structures and algorithms as a course, and where I got stuck the first time was trees. Like I really did not like trees at that point in time because number one, like actually solving them, you majority of the time you kind of have to draw it out. It's quite hard to really just visualize a tree in your head. So the hassle of drawing it out and going through everything step by step, especially when you have like a large input size, I was like, oh my goodness, I don't want to do this. So the first thing I did was actually just search online and be like, okay, is there any like tree visualizer that I can find? And the ones that I found were they had two things, two problems. Number one, they were either like really old, like the UI was really old and not really enticing. I'm someone who, if you have a product and the UI is good, I will love it just from the look of it. So that was one, and then there was also kind of no way to really like step into each single like insertion or the way the tree was building and like see, okay, why did it take this step outside of the fact that you already know the algorithm, right? So that's where this comes in. This handles that, and also the ability to even do some little bit of more research by having helpful links at the end of the day. So enough said, let's get into it to see actually how it works. So this supports multiple trees at the moment, BSTs, AVLs, down to tri trees. I know there are more tree data structures. They might not be as common as these, but we will, by we I mean me, add it later in the future. So going into a BST. So let's say for example you don't even know what a binary search tree is. I have this little I model that is really helpful. Tells you a little summary of what's going on. Okay, binary search tree is a node-based binary tree data. Okay, where each node has at most two children. Okay, the left subtree contains values less than the parent node. So that means if you have one node here, the thing to the left is probably less. If you have another thing on the right, it's probably greater than it is, and it tells you, okay, this is how it works step by step. And real world applications like database indexing for quick lookups, file system organization, things of that nature. You can also learn more about it. So let's actually build a tree. Let's say, for example, I want to build this one, and there we go. So, like I said, the two things that was giving me a lot of problems previously was the fact that UI wasn't great, and there was not really like some form of explanation, that will tell you, okay, why is this going this way? Why is this going this way? So that's where the step log comes in. It's really nice. You can also increase or reduce the speed of the animations if you want to. But so let's say this specific example, let's say we want to make it really slow. And this specific example, you're inserting 35. Um, so 35 is the right child of 17. And if you remember from our explanation, anything to the right of it, to the parent of it is greater, anything to the left of it is less. So carry on. And if you also just want to skip to the end, you can just go to the last step, or at the beginning, just click skip animation. And there's also other operations too as well. So for example, if you want to insert, let's say, a number or a list of numbers, it also supports that. You could just type it in here. So for example, let's say we want to insert 7. We could go through here. I should probably increase the speed, but yeah, pretty straightforward. It tells you, okay, comparing 7 with 10, go left because it is less than that. Compare 7 with 5, go right because it's greater than that. And then, yeah. Deletions too as well. Let's say we want to delete something that does not exist. Let's say we want to delete 100. And 100 does not exist here. So it will search through every single thing, or at least search through, the path that it goes. Um, it's really slow here. Let me increase the speed. And it tells you, oh, okay, we can't find 100 because 100 does not exist in the tree, which is really cool. Um, I think my video might be blocking that actually. Let me reduce this. Yeah, there we go. Okay. Um, Back to this. Yeah, so let's say we want to search for 13. Boom. Searching for 13, go right. Let's make this a little faster. And yeah, okay, we already found it here. Okay, cool. Also supports traversal still as well. So if you want to know how in order traversal works, or pre-order, or post-order, or level order, you can have it there. And then we can do one more example. Let's say, for example, you don't know what a B tree is. Let me pause this. Let me clear. And you can go here to find out what a B tree is. Cell balancing tree data structure, this and that. You can have multiple keys, multiple children, ideal for storage systems, large blocks of data, things of that nature. Here's like how it works, a little pseudo algorithm here for you, and you can learn more through here. So let's have this here. We're building the tree. Tells you step by step what's going on. You can also increase the speed to go super fast. And yeah, so that's pretty much it. I feel like it's gonna be a really helpful tool for someone who's learning trees for like the first time or encountered the same problem that I was going through. There's also a feedback form here. Let me move my camera right here, where you could, if you want, maybe we could support, by we I mean me, support more trees, or just feedback on how the application is. I'd appreciate that. You can put that through here. And yeah, thank you so much for taking time out of your day to watch this. I appreciate you and have a lovely day.